this. Okay, so we talked about just kind of big picture FPGA architectures. So we saw there are a few different logic elements. None of them scale to really big sizes, so we have to connect them together with some kind of routing network. And the first kind of routing network we looked at were hierarchical ones. And hierarchical ones are inspired by the fact that circuits are hierarchical, so you don't need as many wires essentially at higher levels of the hierarchy as the sum of all the wires at the lower level of the hierarchy, which helps you scale your design. And we went through a Rent's rule analysis to see that you didn't have to increase these long top-level wires as rapidly as the total number of the shorter wires. So that was good. We also saw that if your circuit didn't have very good locality, had worse locality than what you assumed would be common when you designed the architecture, the CADs would have to space things out a lot, right? Because you would start running out of wires at these upper levels of the hierarchy, and your only solution is to not use all your logic, which we can do. But we saw that if we designed the architecture for a rent exponent of 0.5, pretty good locality, and instead a circuit had a rent exponent of 0.75, pretty bad locality, we'd have to space out by about 50%. So a lot. We can only use half the logic. So that's one downside of this kind of architecture. If circuits are less local than you thought, you're going to have to space out quite a bit. This is a picture of basically the same kind of architecture I was showing you before. So logic blocks down here, first level wires, second level wires, third level wires, fourth level wires, okay? And if I want to connect a block, for example, here to that block way up there, so a block from this point, let's see. So a block from here up to the block up here. I use a first level wire, then a second level wire, then a third level wire, and so on. And I get across. Is there anything else you don't like about this architecture? Okay, so we talked about some kind of good, follows the hierarchical structure of circuits. Bad, if you don't have as good locality in your circuit as expected, you're going to have to space out a lot. Does this diagram make you think of anything you don't like? What do you think?
I think the level 3 routing
is too. You have too much of it? So what do you mean by too much? So is it that these wires are too long? Do you think there are too many of them? What is it? Wide. So you think too many of them. Well, we do get a fair number of them. That's true. Although, as I showed before, with the total number of wires at this level is less than the total number of wires at the level 1, right? Because we're exploiting this hierarchical nature of circuits and the locality that Rent's rule gives us. So I guess you think, well, I should have put fewer in. So, all right, but then you feel lucky because you feel like customers or designers are going to have good locality in their designs. So this is kind of your trade-off. You do look at these, you go, man, that seems like quite a few wires still, but how many do you want to take out? It's risky. Anything else? Why do you not like these wires in particular? There are more of these ones if I add them all up, these level 1 wires. If I add all these up together, there are more of them than these, okay? But you're picking on these L3 wires. And I'm not disagreeing with you, but why do you not like the L3 wires?
I think more communication happens locally.
Yeah.
I assume that a perfect design, most of the communication happens.
Well, and there is more in this architecture. I've built it for that. I've built 1, 2, 3, 4. I got 8 times 3 L1 wires. So the total number of L1 wires is 24 if I add them all up. And the total number of these L3 wires is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So L3, I've only put 12 in. Okay? So I did actually build more of the L1 wires than the L3 wires. But you still don't like my L3 wires. And I'm not saying you're wrong. I'm asking you to elucidate why you don't like them.
I think L1 wires are supposed to be longer.
Yeah, there should be more of them, for sure.
Yeah, because they are at the lower hierarchy level.
Yeah. So these wires,
And they cost less.
yeah, they cost less. These wires look big, right? So visually they look big. They are visually big because they are big. These wires at the upper level of the hierarchy are connecting relatively distant parts of the chip. So is that a problem? Well, I mean, they are more expensive, so we don't like that. What's happening as we scale semiconductor processes? What do you think? What's happening to wire delay as we make our process technologies, smaller and smaller? Does anybody know what's happening to wire delay? It decreases for, well, what happens if it has to go all the way across the chip? So maybe this is too vague a question, okay? Did you say it's decreasing or? Yeah, so if I have to go, so maybe this is too vague a question. For short wires, okay, so what's happening as we scale our process technology is the wire cross-section is getting smaller, okay? And it's actually getting quadratically smaller, which is driving resistance up. Resistance per unit length is actually going up quadratically, okay? Yeah? Yeah, these wires have parasitics, so they have resistance, they have capacitance, which means you cannot assume these are zero delay at all. Nowadays, wiring is actually more important typically to delay than the actual transistors. The transistors matter too because they're driving the wires, but basically the wires are the big problem for speed. And what's happening is as you scale a process, here I'll draw here's an old process, say, big fat wires. This is the cross section. This is like height, this is width. And if you remember back to your first year engineering, you learned what the resistance of a wire was, and it's length divided by area times resistivity. Okay, so resistivity we can't do much about. We're already using copper. Copper's a really good conductor. Length, as we scale the process, we actually have some good news. The length gets shorter, right? All our circuitry compacts, the wires get shorter, that's good. But this area is bad news, okay? Our resistance goes up quickly because the area, cross-sectional area goes down by the square. If I scale the process down by 0.7, every dimension gets 70% as big as it used to be. My area is actually half. Okay, my length also goes down by 0.7, but it means my total resistance of this wire actually goes up when I scale from that to that. Does that make sense? And then if we go look at capacitance, it turns out that capacitance per unit length also goes down, so that's good, all right, because your delay is actually proportional to R times C. So your capacitance per unit length goes down. For wires like this, I don't get the benefit of this length getting smaller. Wires that just cross the whole chip. If I make a new chip and a new processing technology, I just make twice as many logic elements. So I add another level of hierarchy. Okay, so the top level of the hierarchy still crosses the whole chip. So I get the penalty of this cross-sectional area going down. I don't get the benefit of the wire actually getting shorter because I got to make some wires to connect the top level of the hierarchy. This resistance then becomes a big problem. Okay, and I don't think I have time to go through all the derivation. Capacitance isn't enough to fix it. Okay, capacitance goes down some, but not enough that my RC delay drops. For a long wire, if I actually want to cross the whole chip, it actually goes up. So that's a big problem. The rest of my circuitry is getting faster, and these long wires that cross the whole chip are getting slower. So I have a mismatch. This is going to be a big limit. Does that make sense? So this is a major negative. So we have long wires at the sort of the top of the hierarchy, like the highest hierarchy level. Okay, so basically they have high resistance, they have high capacitance, and that means they're slow. And basically, as we're scaling our semiconductor process technology, like long wires are increasingly bad, right? If we go back, well, quite a few process technologies, they weren't too bad. They are now like terrible. You do not want any wires that cross your chip. So that's a problem. So what we would do is we wouldn't really run a wire this far across a whole chip in a modern manufacturing process. It's too slow. So what do we do instead? Let's say I still want to have this architecture. What can I do with this wire? The problem is basically the longer the wire gets, the more its resistance builds up, the more its capacitance builds up, and its delay is proportional to RC. Okay, and both of those will grow as the wire gets longer. And the constants in front of them are also getting worse as we scale the process technology and the cross section of the wire gets smaller. So we got a lot of problems here. So we wouldn't really build a wire this long. So what would we do? Like any time you have a wire that's going to cross a chip, and there are a few in every chip, we don't really build one big piece of metal. So what can we do instead? Yeah. Yeah. So that's even better. Okay, so you're saying segment this into a bunch of pieces, put programmable switches in so we can break it up. So it's a good idea. I'm going to go only half that way first. So let's say we're going to go the rest of the way in the next section, so you're 2 steps ahead. If I want to go this far, I can rebuffer it. Okay, so to stop the resistance and capacitance from kind of growing too big, I can put inverters in here every once in a while, and that's what you would do. It'll cost me a bit of area, so we're going to need to rebuffer. Okay, so that's going to, it'll stop the delay of this from getting, basically the delay of this wire grows quadratically with its length. So at a certain point, that becomes really slow. Like, you double the length of this wire and it gets 4 times slower. That's terrible because both the R and your C got twice as big because the wire's twice as long. So we can stop that quadratic growth by putting inverters in every once in a while, maybe every millimeter or 2. But that's going to cost us some extra area and power. But we're going to have to do it. But there's basically no great solution here. This also is going to consume every signal that goes over such a big piece of capacitance is going to take a bunch of power too, right? Every toggle of this wire, we charge, when we go to 0, or discharge when we go to 0, then we recharge when we go to 1. If this is a lot of capacitance, that's more power, so we don't like that. So it's not great. So this is probably the number one thing that has been problematic for these hierarchical architectures in recent years is these long wires don't scale that well. So if you make a purely hierarchical architecture like this, it doesn't scale to the really big densities you can get in a modern manufacturing process. Okay, so that's a negative. There's another negative that's kind of visible on here too. It's kind of related. So basically, fundamentally on modern chips, wiring dominates delay. So if we have a lot of wiring between things, it's going to be slow. So let's take these 2 blocks, this block and this block. I can connect those 2 blocks together with just a relatively short level 1 wire. Okay, so that's pretty good. Short wire, relatively fast, relatively low capacitance, low power, it's all good. Okay, so now though, let's say I want to connect this block and this block together. To connect these 2 blocks together, I actually have to go out here, take a level 1 wire, take a level 2 wire, go over here, take a level 3 wire, and back down. So I need a fair amount of wiring to connect those 2 things together. However, physically, they're not that far apart on the chip. Right? So these 2 blocks, well, they've got this wiring in between them, but they're not that far apart. They're adjacent, but I can't connect them with short wiring because my routing architecture doesn't allow it. So does that make sense? So this is kind of a missed opportunity. So another negative is that some physically close together blocks So some blocks that are physically close together are far apart in the routing hierarchy. Does that make sense? So not catastrophic, but kind of seems like a missed opportunity. Nowadays in a chip, you're always, you're trying to keep everything that you can local, because the energy cost, the delay cost, the cost in every way of moving data is large. So you don't want to move it through a lot of wiring if you can avoid it. Okay, so those are some negatives. I can think of one more positive, which might or might not be, might be too hard to guess, but any ideas of like any more positive or negatives for this style of architecture? Yeah, what do you think? Connectivity is guaranteed. It's not guaranteed if I've taken some switches out, which I have here, and if I reduce the number of wires to the upper level. Does that make sense? So it's not guaranteed. If I put a lot of switches in and I really put a lot of switches to the upper level, then I could make it very likely, but it might make my area bigger. But I still think you're kind of onto something. It's not guaranteed, but it turns out the CAD tools for this kind of architecture are simpler than the alternative we're going to look at next. So for this kind of CAD tool, you have some circuit. So you got some design. Your design has a bunch of logic blocks in it that are connected in some way. Okay, so it's normally represented as a graph, or technically it's something called a hypergraph, because you can have fan out. But basically your design to a CAD tool looks like a whole bunch of nodes and edges, where the nodes are blocks and the edges are actually hyperedges. A hyperedge just means it's an edge that has one start point and multiple destinations. So that's a hyperedge, or also called a net. We have to take this and we have to decide where each one of these blocks in my design, where do I put them on this? I might decide this one implements A talks to B, so maybe I'll put B there. B talks to both C and D, so maybe I'll put C and D here. And then D talks to E, and maybe I'll put E over here. Okay, so that might be one way the CAD tool could map this. This is a nice simple one, so I just did that pretty fast. But in a big design, this can be a lot more complicated. So the way the CAD tools that were generally written for this kind of architecture were partitioners. So partitioners take a design and they chop it into pieces. So they'd say, okay, I'm going to draw a line through this that cuts as few edges as possible. Okay, so I just found an edge, a line here that only cuts one edge. And I say this goes in one partition and this goes in a different partition. Okay, and so now maybe I put A and B up here and I put C and D down here. So you start by cutting the circuit in half, and that decides, actually let me do this differently. So to make this look better, I'm going to go like this, C, D, and E, okay? Or maybe I'll go even better. I'll go C over there and D and E here. This is a better partitioning. So my first cut, I'm going to say, was here. That first cut decided this half of the circuit is going to go over here, and this half of the circuit is going to go over here. And then I cut it again, and my cuts are now pretty easy. That one, logic block A and B, and this one I'll cut, and I'm going to get C on one side, and D and E on the other, and then I'm going to cut again, and I'm going to get D there and E there. Okay, so that was probably a very fast visualization of how a CAD tool works, so don't worry if you didn't catch all the details. Partitioners are CAD tools that are pretty fast. Okay, so it turns out that this algorithm to decide how do I cut this circuit in half so that I don't cut many edges, that's what a partitioner is trying to do, because I'm trying to minimize the amount of wiring between these two halves. Those CAD tools are pretty fast, they work pretty well. And by running a partitioner over and over again, I can naturally divide up a circuit and then it maps it to this hierarchy. Okay, so I cut it in half went here, the other half went here. Cut it in half again, this piece went there, this piece went there. Final cut, this piece here, this piece there. So the CAD tools, this is an advantage of these. So CAD Flow can use partitioning. Let's see, I actually wrote a couple of notes on this. well, whatever. CAD flow can use a partitioner. And these tend to be fast, and they get good results. And that's one of the reasons people like this kind of architecture. That advantage, though, is generally not enough to make these the best architectures, at least for big FPGAs in state-of-the-art manufacturing processes, because of these really long wires. That's kind of the Achilles heel of this. So there's a company called Flex Logic. It makes embedded FPGAs, so you stick their FPGA cores inside a larger system on a chip. It means their FPGAs aren't that big. There are a few thousand lookup tables, or maybe tens of thousands of lookup tables, instead of millions that you'd get if you buy a really high-end FPGA. Flex Logic uses this architecture. So as long as you don't need to make the chip, scale to really big densities, this works fine. But if you need to scale to really big densities, then these long wires start to really hurt you. Okay? Does that all make sense? Okay, in that case, I'm going to see what I have on the next one. Okay, so I'm going to talk about the alternative. So the other big class of routing architecture is island-style routing architectures. Okay, island-style routing. And this is a picture of it. So maybe I'll draw a little, I'll let you look at that for a moment, and I'm going to draw another picture here. So, okay, so actually I'm going to turn off the projector. And I'll draw you another picture. Okay, so what does this look like? That's one too many. Okay, so with this kind of architecture, we take logic blocks and we make like a two-dimensional array of them. And in between the logic blocks, we put prefabricated routing wires called routing segments. And then we put programmable switches to allow us to connect the outputs of these blocks and the inputs of these blocks to some of the wires that go past them. So I'll draw a few programmable switches there. Usually we do this in a regular pattern to kind of make this easier to lay out. So we'll make a layout for one tile and then repeat it over and over again to get our pattern. Okay, and so far I haven't connected these routing wires to each other. So we also I'll just draw dashed lines to show some of these routing wires can also connect to each other with routing switches. Okay, so I'm not going to draw them all, but maybe there's some routing switches between these, and so on. Okay, so we've got routing channels around the logic blocks. Okay, let's define a little terminology. Okay, so those routing channels are filled with wire segments. Okay, so wire segment, piece of wiring goes a certain number of blocks. So we usually say they have, so usually we make different lengths of wire. So this would be called length 1 wire. Only goes past 1 block, and you have to go through a programmable switch to keep going. This would be a length 2 wire. Goes past 2 blocks, and then you have to go through a programmable switch to keep going, and so on. So, okay, so usually several lengths. Okay, we don't normally talk about their length in millimeters. We talk about it in terms of how many blocks they go past, like what's the topology. Okay, and then the last thing, so we got these channels. The channels have wire segments in them, and the last thing we have is we have these programmable switches. And we have kind of 2 types, so they serve 2 purposes. So some of them connect wires to the IOs of these blocks. Okay, so that's what I drew with these little X's. And then the other kind of programmable switch which I drew as dashes, connect the routing wires to each other. Okay, and then the last terminology is we care about how many wires we put per logic block. That affects our area. More wiring means more area. It's also going to make it easier for us to connect up circuits. So the channel width is how many wires do we put in each of these channels. So here the channel width is 2. And we usually give that the variable W. Okay, so W wires per channel, and here W would be 2. Okay, so I'll move this up here. All right, so hopefully all the terminology is clear. Not ask me. Any advantages or disadvantages of this? So we just went through this for hierarchical FPGAs. What do you think? What's good about this? What's bad about it? There's got to be some good things about it because most modern FPGAs use this style. Okay? Yeah, what do you think? So basically the fact that you've got some longer wires means that your delay doesn't grow as quickly. You can kind of go past them. Yeah, so that makes sense. And you kind of have quite a few options. You have some short wires if you're not going very far. You have some longer wires if you are going farther. So you kind of have more options about how to get from A to B than you had in a hierarchical FPGA. And that can be beneficial. So anything else you like about this? Let's think about the wiring resistance and capacitance we talked about. Like the hierarchical FPGA had some really long wires that got physically difficult to fabricate. Well, you could build them, but they weren't very efficient. What about this one? Is it going to have long wires that are hard to fabricate or not? That might be an unanswerable question. You can take a shot at it. So I maybe haven't told you enough detail. Like, I don't have to. I mean, I can choose what the lengths of these different wires are. I just won't make any wires that are so long that they're really inefficient. And this actually goes to your answer during the hierarchical FPGAs of why don't I basically instead of making some really long wires, break them up at the point where the resistance is getting too much and put programmable switches in between them. And if those programmable switches include a buffer, an inverter, then I'm going to stop them from kind of building up resistance and getting really slow. So I can avoid building really long, slow wires that are problematic. I can still get all the way across the chip when I need to by connecting up the wires using programmable switches. So I've got kind of more options. So I guess one of the ways I would talk about this for an advantage is the inspiration for this kind of architecture. Okay, so the inspiration for hierarchical architectures was that circuits are hierarchical. So let's make something on a chip that looks like that. The inspiration for this one is that chips are two-dimensional. So if we build an architecture where things that is two-dimensional, right? We basically can make things that are physically close can connect quickly because we're kind of closer to the physics. So let me write that down. Okay, so a positive here is, yeah, it's kind of a 2D architecture driven by what manufacturing technology gives us. So we have physically close blocks. We have fast routing. Now we can connect them with short wires, or if they're not quite so short, maybe a medium length wire. But if you're close, we can build some options where you won't use much metal. And your capacitance will be lower, your speed will be higher, your power will be lower. So we can get fast routing. Whereas in the hierarchical FPGA, this was only true for sort of some blocks that were close together. If they're physically close together and they were near each other in the hierarchy, then you got fast routing. Here, if you're physically close together, there'll always be some fast routing choices. Now, the downside of that could be that maybe you go all the way across the chip, which is going to happen once in a while. Could be really slow, and that's mitigated exactly the way you just said. So to mitigate, what about going a long way, is we have these longer segments. So that means that you'd rather not be far apart, but far away blocks still have a reasonable routing choice. Okay, you might still have to connect a bunch of, you might have length 8 routing segments that go past 8 logic blocks, and you might have to connect quite a few of those together with programmable switches to get all the way across the chip. But the truth is you can't do it that much better, no matter what you do, because you can't make one really long wire to go across the chip. You got to go through some buffers anyway. So in this case, if we're going to go through some buffers, why don't we go through some programmable switches on the way? It's going to cost us something, but it's not going to be too bad. Okay, does that make sense? And this has been kind of the key advantage for big chips. So this dominates for big chips. Okay, so another advantage, which is maybe hard to see, is scalable. Okay, so we looked at this for hierarchical FPGAs. As we made the chip bigger and bigger, what was happening to our routing? Did we have to add a lot, et cetera? So let's do the same kind of analysis, Rent's rule analysis for this kind of architecture to see what happens as we make it bigger. And to do that, I want you to consider kind of a square array of logic blocks. And this array it's m rows high, and it's m columns wide. Okay, so that's what you're considering. An array that is m by m. Okay, so it's okay, so I'm basically going to change m. So I'm going to gradually make this array bigger, because I want to see what happens to how much logic I got inside this array and how much wiring I need inside the array, so that I can get a sense of, is this scaling well, or am I basically having to increase the wiring way faster than the amount of logic, which would indicate this doesn't scale very well. It's going to get really inefficient if I make it big. So to do that, I need to figure out, well, how much logic is in here. So logic, or gates. This should be the easy one, okay? So how much logic do I fit in this m by m array? Squared? Yeah, it's just m squared, okay? So this is the easy one, okay? So we got m squared logic. We'll assume every logic block implements 1 unit of logic. How many wires? Now I need to think about how many terminals. I need to think about how much wiring comes out and goes into this, okay? Because that's going to affect how many terminals I can handle. Does that make sense? Rent's rule, I'm going to use Rent's rule. Rent's rule relates how much logic I have in something to how many inputs and outputs I need. So, okay, so this is only slightly harder. How many wires, so these routing wires that are coming in and out, how many of them are crossing this boundary? Okay? I'm going to draw it so it makes it easier. Okay? So on every side, I'm going to have M routing channels. Every logic block comes with a routing channel that goes beside it vertically and another routing channel below it that goes horizontally. So if I look at this side, I get 1 vertical routing channel, 2 vertical routing channels for M equals 2. And if I made M 4, I would get twice as many. I'd get 4 vertical routing channels. Does that make sense? All right, if I do the same thing for the horizontal routing channels, there's 1 below, another 1 below here, so I get 2 on this side, and in general, I get M on this side. There are 4 sides, okay? So the number of wires, okay, let me write this down differently. So wires, that enter or leave is equal to 4 sides times, on each side I'll get M routing channels that cross through my perimeter, and each of those has a number of wires in it of W. Make sense? Okay, and I'm going to call that, I'm just going to define that to be W supply. Okay, like the total amount of wires I could ever possibly use to get in and out of this block of logic. In practice, I probably can't use every single one of those wires because there'll be some blockages. I don't have switches that can get at every single one of them independently. So maybe I can only use half of them at any one time. But it doesn't matter for this because this is like an asymptotic analysis. So it doesn't really matter if you say, well, a real circuit, if you try to use every single routing wire, you'll get some blockages and it won't work. Nothing changes this in analysis if I just say I can only use half of them. Okay, so I know how much total wiring I could possibly get in here. I know how much logic I've got. Now I'm going to go to Rent's rule. So Rent's rule says the number of terminals is equal to some constant times the amount of gates that are in my logic to the Rent exponent. Okay? I'm not going to work in gates. I'm going to work in logic blocks. So I'm just going to rewrite this. That's just some other constant times my number of logic blocks, which is M squared. And so I've just replaced G to get this new constant and M squared. And G is supposed to be taken to the P. Right? It's supposed to take my total amount of logic and take it to the Rent exponent to figure out how many terminals I need to get in and out. Okay, and we're going to define that to be the wiring demand. Okay? Everybody with me on this? Sounds good? It has the right behavior. Like remember, if P is small, we have a very local circuit. Well, then this is going to make a small number of terminals. If P is 1, the worst Rent exponent, well, then our number of terminals is going to grow quickly. It's going to grow with M squared. So hopefully that all makes sense to you. Okay, so for this chip to successfully route as we make bigger and bigger versions of it. So we're making M bigger and bigger and seeing, well, do we hit a point where we just can't get all the signals in and out of this region of logic? What we need is we need W demand, or the wiring demand, to be less than or equal to the wiring supply. And for that to be true, I'm now just going to write in what I have for each of these. So I said this is wiring demand, some constant times M to the 2P. And that has to be less than or equal to the wiring supply, which is said is just the perimeter, 4M times the wires per channel. Are you with me on that? Okay, so that sounds good. I see some nodding at least. So I want to solve for W. That's the number of wires per channel. I care about what happens to that as I make the chip bigger and bigger. I want to know if I need to make my wiring channels really huge, which would mean I'm getting, as I try to scale up this array and make a bigger FPGA, if I have to make the routing channels really wide, it means I'm getting less and less efficient. A larger and larger fraction of my area is actually wiring, and less is logic. But I sell these chips by logic capacity, right? I need to have enough wiring that they work, but I really sell them by capacity. So let's just solve for W. Okay, so I'm going to divide by 4. So I got C prime divided by 4. We divide by M. So that's just M to the 2p minus 1. And that is less than or equal to W. Okay, so I need to make my channel width greater than this in order for circuits to route. And it's a function of the rent exponent. So it depends how difficult a problem do I want to make work. Circuits with higher rent exponents are harder to route. So let's just plug some numbers into this. So if we said that the rent exponent being less than or equal to 0.5, rent exponent is always between 0 and 1. And we said a rent exponent of 0 corresponds to like a linear pipeline. Really fantastic locality. A rent exponent of 0.4 corresponds to a circuit that can be laid out as kind of a 2D array, like an SRAM or some kind of two-dimensional systolic array, which is pretty good locality as well. So if my rent exponent is 0.5 or lower, this 2p minus 1 is actually 0 or even negative. Negative doesn't really make that much sense. Well, basically 0 is good enough, right? So if my rent exponent is 0.5 or lower, W does not increase with M, right? It's proportional to M to the 0. So it's constant. Okay, so for these nice circuits with good locality, we have a constant W, okay, as we increase M. So that's actually a great result. So for circuits like that, we never get less efficient. We just keep stamping out the exact, we make this basic tile with a certain amount of logic, a certain amount of routing, and we can stamp out a 10 by 10 array, and then stamp out a 100 by 100 array, and then a 1,000 by 1,000. They're all going to work fine, right? So that's great. Don't have to relay it out. We never lose efficiency. So it's really good. Now, not all circuits, this is pretty good locality. Okay, so some circuits are this local, but most aren't. So let's take worst locality. And we said last week the rent exponent of 0.75 is pretty bad. Okay, it's not the worst you could get, but it corresponds to a lot of random logic that connects in all sorts of complicated ways. If we plug that in, we get 2 times 0.75 is 1.5. Subtract 1, we get 0.5. So our wiring, in that case, it means W would have to be growing as the square root of M. Okay, but notice that the amount of logic we're getting in is actually proportional to M squared. So in terms of logic, or the number of blocks in our chip, is it 1 million blocks? Is it 100,000 blocks? It's basically proportional to n blocks to the 0.25. Okay, so the 4th root of the amount of logic. So this is actually pretty good. All right, this is actually a pretty difficult class of circuits, pretty poor locality. And it says, yeah, if you want to keep making bigger and bigger FPGAs and they can continue to route these circuits, you will have to increase your channel width, but actually quite slowly, only the 4th root of the size of the FPGA. So let's see, what does 4th root mean? If I had something that is, let's see if I can do this properly. So yeah, I've had one device that has 1 million lookup tables and another that's 16 million lookup tables. The one with 16 million lookup tables would need routing channels that are twice as wide, which is not trivial, but it's not terrible for that huge density range. In practice, this is pretty poor locality. So the channels in commercial FPGAs actually grow even more slowly than this. So if you track over time, you'll see that the channel width has been slowly increasing as you make bigger and bigger FPGAs. But it's even slower than this because most circuits are kind of in between these two. So the target is probably more like a rent exponent of 0.6 or so. Does that make sense? So this is pretty scalable. Okay, so slowly growing W, which is good. Now with capacity. In practice, whole circuit's not usually 0.75. There are cases where it is, but they're not common. So you can grow W even less than that. You do definitely get random logic pieces of a circuit that are, rent exponent of 0.75, but your CAD tools can usually just space those out. Okay. So I've been talking about this like a whole circuit has one rent exponent. You can have sub-pieces that behave somewhat differently. The control logic is usually worse locality, but again, the CAD tool can just find those pieces and space them out. You need a reasonably advanced CAD tool to do that though. Okay, so what this means is W nearly constant. As your array grows, if you have good placement. So placement is the CAD phase that chooses where you put all the blocks on the chip. So I showed you that net list of this is what I need. Here's my million lookup tables and how they should talk to each other. The placement algorithm says, okay, you've got 1 million lookup tables that you need. I've got 1 million or maybe 1.5 million on the chip. Let's choose where they go. That's a difficult problem. If you have good placement, you will get better locality for the vast majority of circuits than 0.75. So good placement means the CAD tool finds what's connected and puts them close to each other. And that's a computationally hard problem. Can't be solved perfectly in any reasonable runtime. So this is why FPGA companies spend a lot of money on CAD. They have big software divisions. Some of you may come from those software divisions because they need to have good placement. If you have a random placement, let's say you just decide, I don't want to invest in good placement. I'm just going to work on the hardware. We'll sort out the CAD tools later. It's actually a relatively common strategy for startups, but it's not a good strategy. If you have random placement, then your rent exponent is approximately 1. Okay, you have really poor locality and like nothing's going to route. Okay, you would have to increase the width of the channels really rapidly. So that is essentially a negative. So a negative of this style of architecture is you need good CAD tools. So the hierarchical FPGA CAD tools we saw, we could use partitioning to decide where to put things. Also the routing problem, like choosing which wires to connect things is actually simpler because there are fewer choices. So the CAD tools for hierarchical FPGAs are typically not as complicated as the CAD tools for this style of architecture. So you need a very good placement algorithm. You also need a very good routing algorithm. So let me erase this too. Okay, so we have lots of routing choices. Okay, so we've got short wires, we've got longer wires. They're connected by these kind of complicated switch patterns. And we can make all sorts of choices of how to connect things. So I want to connect from here to there. You know, I might do it like this, to here, and in. But that's not the only choice. There are lots of other choices. I might instead come out here and go here and, you know, around and so on. Okay? So there are a bunch of different choices. So that's kind of a strength of you have lots of options, but you need a CAD tool that can explore those all quickly. So you need a good router, and it has to be timing driven. Okay, so timing driven means it figures out what are the speed limiting paths of your circuit, and it gets them fast routing. That's really important in this kind of architecture because there will be some paths that are fast. You know, they use a small number of wiring segments that are the appropriate length and so on. And there'll be a lot of paths that are not fast. So if you have a routing algorithm that doesn't do a good job of prioritizing who gets the fast routing and what all the choices are, you'll get a very slow result. So you need good timing-driven routing. So, I mean, I joined Altera by, we actually redesigned some of their CAD tools. For their architectures at the time that I joined them were partially hierarchical. Okay, so they were hierarchical architectures, but not quite as rigid as what I showed you. And we developed new CAD tools that were not based on partitioning, that essentially could exploit the fact that some of these wires were getting slow, and therefore the delay, if you went a little way along the wire, was not as much as if you went a long way away. And they worked better than Altera's CAD tools, so they liked them and they replaced their CAD tools with those new ones. And then we told them, because we're still a separate company at this point, that these are the wrong chips for these kinds of CAD tools, right? If you let us design the chip, we'll do something more like this, which is what the Stratix series and all of its follow-ons look like. And by giving more choices to the tools, we'll get you better results. And they had actually analyzed this kind of architecture, these island-style architectures, and they concluded they were bad. But the reason they concluded they were bad, well, we're pretty sure, is because their router wasn't good enough. Okay, their router didn't do a good job of sorting all the options. So when they did experiments with these kind of chips, they decided they weren't as fast. So we did redesign their architectures to this style. We deployed the CAD tools that my company had created, and they did work better, okay? But the reason I bring that up is like, yeah, it's evidence that you really do need good timing-driven routing, because that delay was probably a pretty expensive mistake for Altera, and it was driven by a bias in their CAD tools. Their CAD tools didn't know how to exploit that kind of routing well enough. Okay, and the reason is basically it has more diversity of routing choices. So if your CAD tools can evaluate all those choices efficiently and they can exploit them, if they don't evaluate them in a very good way, then this is a hindrance. This is why the big FPGA companies like Intel and AMD use this kind of style, island-style FPGA now. And that's partly because it scales better to really big chips, and it's also partly because those two companies have very good CAD tools, right? They've made investments of, I don't know, hundreds of millions of dollars over the years for sure in CAD tools, maybe more than that. For startups like Flex Logic, okay, they don't have the same budget for CAD tools, and they're doing smaller embedded FPGAs. Hierarchical FPGAs make sense to them. Keeps the CAD tools simpler, and we don't need to go to the really big designs. Okay, but this is the dominant style of architecture we're going to look at in the course.
I have one question.
Sure. Yeah.
The time that you use this routing architecture to build it up,
Yeah.
what did Xilinx have?
So Xilinx always liked island style. Okay, so Xilinx and Altera went in opposite paths. Xilinx's island style architecture started out simpler. They gradually added more complexity to them. So it wasn't like they were always the same architecture because they used that style, but what went in the logic block, how the routing worked, changed. Altera started out with hierarchical FPGAs, and they gradually also made those more complicated, like kind of adding more levels to the hierarchy, changing it around, making it not quite as strictly hierarchical, but they were still, there was a significant difference of where each of them was.
How could Altera conclude that this architecture is bad, given that it was working for Xilinx?
Well, you don't, given that your competitor is using that style of architecture, you should look at it, you're right? Because if you don't look at it, you could say, well, you're super self-assured, but actually you're probably just overconfident. So they did look at it, but that's just because your competition's doing it doesn't mean they're right. Okay, so they looked at it, but they looked at it with their CAD tools and concluded it wasn't as good. And actually, for a long time, also, Altera's FPGAs were outperforming Xilinx's. So and this is partly. So yeah, so they also had like, well, our chips are faster, right? They're routing with a higher percentage success rate. We're making market share gains. It's all going well. But some trends were against them. As exactly what I showed you. Every generation, you're going to the next process node, the chips are getting bigger. As the chips are getting bigger, those long wires are becoming more of a problem. So that's something that was essentially helping Xilinx, like physics was helping them. Physics is a tough thing to fight, right? So go out, try to fight gravity, not good. The other thing is CAD tools in the industry were getting better. Okay, so Xilinx's CAD tools were gradually getting better. So were Altera's, but there was essentially more upside in their architecture. And that was an interesting thing. So it wasn't like this so what this architecture could do, even the same hardware for Xilinx, was changing over time as their CAD tools got better at exploiting it. Does that make sense? That's a good question. So I had to think about the answer to that. So, okay, so let me talk about the last one of style. Okay, so you're an engineer, you got two different options. All engineers think, what if I combine them both, right? Maybe I'll combine them both and I'll get the best of both worlds. So, okay, so we can think about that. So we can make a hybrid architecture that combines some features of each of these things. Okay, let me give you two ways we could combine these. So one way we can combine them is we could say, we're gonna make little island-style FPGAs, and those are gonna be like our new logic blocks. And then we're going to connect those logic blocks together with the hierarchical routing to make the whole FPGA. So that's one way. Little island-style FPGAs and then stick them into hierarchical routing. Or we could do the opposite. We could make little hierarchical FPGAs and replace these replace individual lookup tables with like simple hierarchical FPGAs that we call our new logic block, and then connect those together with island-style routing to make the whole FPGA. Does that make sense? So what goes at the small scale, what goes at the big? Which of these hybrids do you like better? One of them works well, right? Otherwise I wouldn't have put this up here. Any idea, or did I just confuse you with the two choices?
Small scale, I think, will be hierarchical.
Okay, so you want the small scale hierarchical and the big scale island style. And that makes sense, right? Because island style, the big benefit is it scales well. So you want the big thing that you're replicating to be island style. The other one would be an abomination, right? Like is it the best of both worlds or the worst of both worlds? And the other architecture would actually just be the worst of both worlds. Like you have all the disadvantages, none of the advantages. So I was actually visiting a customer when I was at Altera years ago, and one of our senior marketing people was there. And the customer asked a question about, at the time Altera had hard copy, so they would do an ASIC conversion for you. You had your design that was going in an FPGA, and your company was doing super well. You're going to high volume, so you're like, well, maybe it's worth putting this in an ASIC. Hard copy was a program by Altera to say, well, instead of going to somebody else to make the ASIC, we'll make it for you. And because we can use some of the IP blocks that are in our FPGA, we can do it faster and easier. So one of the customers asked, well, could you combine that? Could you give me something that's half FPGA and half hard copy ASIC? And the marketing person answered, I have two words for you, amphibious car, right? And he goes, without knowing anything else, you know this is a bad car and it's a bad boat. So that was an example of actually taking half FPGA, so you get the cost structure of an FPGA, and half ASIC, so you get all the inflexibility of the ASIC, is like the worst of both worlds, right? We've got a very expensive ASIC or an extremely inflexible FPGA. So yeah, the one where we make small island-style FPGAs and connect them in hierarchical routing would be like an amphibious car. You don't want that. So, but this one works. Okay, so the advantage of hierarchical is we get simpler CAD, but the disadvantage is we had poor scalability. So what we can do to kind of overcome that is we can use hierarchical at the lowest level of the hierarchical. At the lowest level of hierarchy. You know, make little FPGAs. Okay, so because we're only making a little bit hierarchical, the wires are still short. And what we do is we group what we call, often the academic community calls these basic logic elements. It's just like LUTs and flip-flops, basically. So we group little bits of logic. Okay, so those logic elements are LUT plus flip-flop that we had before. Basically, going back to the question of Xilinx, Xilinx FPGAs for a long time used individual LUTs, or maybe a couple of LUTs, as their logic block. So their logic block was essentially like a logic element. It was very small. And then you connected everything together with the island-style routing. So instead, we could take those really small logic elements and group them into what are often called logic clusters. Okay, so they're logic blocks, but there's sometimes called logic clusters to kind of differentiate. They're a bit more complicated. There's more stuff in these. Okay, and then we're going to use island-style routing in between them. Okay, so what does this look like? Okay, so we've got a basic logic element, which is basically a LUT and a flip-flop. So it has a clock, and it has a few inputs coming in to go into the LUT. And instead of, so what Xilinx was doing was just connect, you know, in its earlier architectures, it was just connecting this directly to the programmable routing. So that's the whole logic block. These hybrid FPGAs basically don't do that. Instead, they make a bunch of these. And the number is usually denoted by the variable n. Okay, so we make n of those. Each of them has, let's say each of them has one output. Take all those outputs, so there are a total of n of them, and they can feed back to the inputs. So this is like a very simple hierarchical FPGA. My outputs can feed back to my inputs without ever kind of going out to the island-style routing. Okay, so there are programmable switches here. Same thing here. There are also some signals that are going to come in from the programmable routing. Okay, so we have some number of signals, say I, that we can get in. And instead of connecting straight to the inputs of these basic logic elements, we basically have those drive some wires that also can connect to the various inputs of these BLEs with programmable switches. Okay, we draw a box around this whole thing. Okay, and this whole thing is called a logic cluster. And it's basically like a very small, single-level hierarchical FPGA. So this is some local routing. It's like your level 1 routing. And normally we don't need things like clock signals. Don't typically go to just one register. Okay, so if you have a clock that only, if you have a whole bunch of clocks that only go one place, it's somewhat of a strange design. Okay, you should look at how you're writing your RTL. So usually your clock goes to a whole bunch of different registers. So we can also do things like have special clock inputs. Okay, so we've got a clock input here, which basically goes to all the inputs of each of these BLEs, rather than kind of going into this local routing and using a whole bunch of programmable switches, which would cost more area. Okay, so that's what this looks like. So what are some positives? So positive is that this local routing is actually quite fast as long as you don't make the cluster too big. So it's typically faster than the island-style routing for this small hierarchical FPGA. Okay, so local routing fast. For basically small to medium clusters. How big is that? Well, maybe based on commercial examples and academic research, maybe 4 to 32 BLEs. Okay? That's kind of the range that you'll see academics investigate and also commercial architectures using. Okay, another positive of this. I said that the island-style FPGAs need more complicated CAD flows. This can help simplify your CAD flow because you can group these BLEs together. This local routing, you can choose to make it kind of simple. It's just one level. There's a lot of switches. So you have pretty good connectivity. It allows your CAD tools to basically group together these BLEs and then make the rest of essentially make the placement problem smaller. So positive of this is it can simplify the CAD flow. Okay, so to simplify the CAD flow, basically you don't have to do this, but you can choose to do a clustering step, which is the same thing as partitioning. You're just trying to find things that are not you're trying to cut up your circuit so that not many nets are cut but go between partitions. But for classic hierarchical FPGAs, you started by cutting the circuit in half, and then you cut the halves into quarters and so on. Clustering is the same problem, but instead of cutting it into a few things, you're cutting it into a lot of things. And usually the algorithms that are used are a bit different. So we can use clustering, which is related to partitioning, but it is trying to make a lot of partitions, a lot of clusters. So we can cluster to logic clusters. Why is that useful? Because it makes a smaller placement problem. Okay, now instead of placing individual LUTs, you can just place logic blocks. And that would mean that you would have faster CAD. And that matters because as these chips get bigger and bigger and CPUs are not getting much faster anymore, the run times of these CAD algorithms for big chips tend to be hours to sometimes even more than that, which is a pain, right? So you also have to think in your architecture about how difficult it is for a CAD tool is a relevant problem because you don't want the CAD tools to run for too long. Now, you could potentially still get this CAD speed-up benefit without logic clusters by just grouping together parts of your circuit and choosing to place those in certain regions. But it's easier to do it if the architecture really has these clusters because they give you a natural boundary to group things together. Does that make sense? Okay, I see some people are with me. Okay. Okay, so another positive. What about this clock? Does this seem like a good thing? That I can take the clock and just hook it up to all the BLEs in there? Seem logical? I guess I told you it's logical, right? So that's another advantage. So this gives us a natural way to support kind of word-wide or shared signals. So clock is maybe the most obvious one. So we can share resources that don't need that much flexibility. Okay, so the inputs to a lookup table, you tend to have to control all of them. You don't know what logic function you're doing. You don't know what signals you're ANDing or ORing or XORing. There's all sorts of different things that happen. But clocks tend to have fan-outs of tens, hundreds of thousands of registers. So to say all of these registers in this logic block, which should have been put together by the CAD tool because they kind of have something in common, share the same clock is not much of a restriction. And it saves a fair amount of area. Because you notice on this clock, I don't have these programmable switches. These programmable switches represent multiplexers. They cost area. And I didn't put any here. I just brought the clock in once. I didn't bring in 10 signals from the island-style routing. I brought one in, and I didn't put a lot of switching on it. I just hooked it up to everything. So that saves me area. And as long as that matches what circuits need, it's good. It's a good choice. So a lot of the signals that go into flip-flops are control signals. So I got a flip-flop, it's got a D signal. Every flip-flop tends to have a different data input. So this would not be a smart one to share. The D input to the flip-flop is going to come from this local routing with a whole bunch of switching. Okay, so I have maximum flexibility. And every single one of these can pick a different D input. If they're all picking the same input, why do I have all those registers, right? I should just have one. But when you get to the other signals, so most FPGA registers have a synchronous clear. They have a clock enable. They definitely have a clock. And basically all these signals they're typically at least shared over like a whole word. If you have a 16-bit piece of data, you're either updating it in a clock cycle or you're not. But all 16 bits are going to do the same thing. If you're clearing a 16-bit register, either all 16 registers get cleared or not. And then clock, as I said, is shared even more broadly usually. It's not just like this 16-bit word shares the same clock. It's like all the communicating logic around it shares the same clock. So these are basically these word-wide signals. It's excessive to give separate wiring to each of them, separate programmable switches, etc. So what you can do instead is just force those signals to be broadcast throughout the whole logic cluster, and you save a bunch of area. Okay, and then the last one is probably very hard to guess. Okay, modern FPGAs don't just have logic blocks. So they have logic blocks, they have RAM blocks, obviously they have I/O blocks, they also have DSP blocks that are multiplies and often a bunch of other stuff in with the multiplier. A lookup table is pretty small, right? Like say you've got a lookup table that's got 4 inputs, 1 output, and a register after it. That's not that big. If you compare that to a RAM block that might have 8 kilobits of RAM, the RAM's a lot bigger. It also has a lot more inputs and outputs. Same thing if we do the same analysis for a DSP block. So if I was to take individual BLEs, individual LUTs, and put island-style routing around them, okay, I can do that. It's got some downsides, like I just said. But then if I say, okay, now at a certain point, certain column, I want to put a RAM block in, or a bunch of RAM blocks in, and the RAM block is like that. It's actually a lot harder to figure out how to make this routing work. I got these tiny things that, we're going to talk about this later, but they'll work fine with narrow routing channels, And they got this big thing with lots of inputs and outputs that will not work well with a narrow routing channel and is not pitch matched. Like it doesn't fit in the same height. So this is a real pain, right? Having blocks that are just different in size. So by grouping these together, your logic cluster is closer in size to your RAM blocks and your DSP blocks. Okay, and that makes it easier to lay out. It also makes it easier to basically choose one routing channel design that'll work for everybody. Make sense? Okay, as we scale process technology, so we keep scaling, right? FPGAs are down at, latest FPGAs I believe are now down at 7 nanometers. It's getting hard to tell what's what nowadays in process technology because both TSMC and Intel have figured out that you can, if you make any variation on your process, you should change the number. So it's not clear how different 7 is than 9 or than 10. But anyway, there are FPGAs now down at 7 nanometers and they keep scaling. So as we keep scaling, wiring resistance keeps going up. So these wires are not that long inside these logic clusters. But as we keep shrinking, even these wires can start to show significant resistance effects, meaning they might still be too long. Okay, so some architectures are starting to make essentially a more complicated hierarchical FPGA inside of here because the long wires, even these wires that aren't that long, can start becoming problematic. So that is a trend that's going on, as we move to really advanced process nodes. Okay, so any questions on any of this? Yeah?
So, like in industry, is there a trend that they're moving to hybrid or to stick to hybrid?
Hybrid is now dominant. Okay, so Altera, basically, because they had hierarchical FPGAs, they used logic blocks like this for quite a while, okay? And Xilinx used little logic blocks, like lookup tables, maybe just one lookup table and then maybe two, but not with any local routing. Now Xilinx uses little hierarchical FPGAs like Altera did. So they've moved to a hybrid architecture. They've almost in their latest generation, so for many years, Altera used exactly this. Okay, it was like a one level of hierarchy. The local routing was very easy to understand, et cetera. And in their latest generation Agilix, they've said, well, some of these wires in 10 nanometers and 7 nanometers are starting to get a bit slow. So they've started making, essentially some of these wires only go half the height and some go the full height. So it's like a two-level hierarchy kind of. They've made their hierarchical FPGA inside the cluster a bit more complicated. Xilinx basically went the other way. They've gone to this kind of more complicated logic block, but their local routing was more complicated. Okay, their local routing had a more complicated set of wires, and it was easier for there to be blockages. And then in their latest generation Versal, they basically said, we love local routing, and they've made their logic cluster 32, actually. They made the biggest logic cluster of anybody. So it's kind of interesting. Altera, which for many years has used this, said that at 10 and 7 nanometers, they see some problems. So they started putting in these shorter wires that kind of make it two levels of hierarchy. And Xilinx basically said at 10 nanometers, this is out of control. This island-style FPGA is too big, takes too long to route, and we got to stop so many signals from going out to the regular island-style routing, so we need to have bigger logic clusters, and we need to have more local routing. So it's actually kind of interesting. Like, this is actually also the question of, like, if you see what your competitor's doing, shouldn't you always do that? Sometimes competitors cross, right? Like, you'll kind of go, like, each of them goes, the other one must know something I don't know, and like you'll have a generation where they kind of almost change roles. That's a little too strong to say that that happened at 10 nanometers, but there's some of it where Xilinx kind of went more Altera than Altera, and Altera decided to go a little bit towards Xilinx. I saw this happen actually once before. Well, I saw a more extreme example of this. You guys can tell me in the course of vowels whether these random digressions are annoying or not. It was actually the ARIA 10 clocking architecture. It's like the last chip I worked on before I left Altera. So we're going to talk about clocking architecture in another couple of lectures, but basically Xilinx had one way of doing it, Altera had a different way of doing it. And part of Altera had decided Xilinx must know something we don't know. So IC Design was like, we're just doing it the Xilinx way. And one of the members of my team who did a lot of analysis of this went, this doesn't make sense. It's actually not a good choice. But he wasn't getting anywhere. Like they were like, no, they must know something. And then the next generation Xilinx chip came out and it adopted the Altera style clocking architecture. And at that point, he won the architecture. Like he won the argument. They're like, okay, I guess you're right. We won't change it. But it was pretty interesting. So they came very close to just changing roles, right? So, okay, so why don't we take a break for 10 minutes, or let's take a break to 5:40. So they get a 7-minute break and come back. Yeah.
Just a random question. With like the increasing resistance on like the longer length wires, are CAD tools ever like leveraging like paralleling to cut down on the?
Oh, that's a good question.
Path signals?
There have been a couple of academic papers that have tried things like that. Have they ever tried parallel or not? I think there's one that's tried that. I don't know of any commercial tool that tries it though, because there's a significant power implication and routability implication to that.
Yeah.
So you'd also need the switch patterns to kind of support it. So I don't know of any tool that is actually doing that though. Cool. Okay, so let's break for, I guess, maybe 5:41. I'll give you an extra minute as I'm being a little cheap today. There's a new one, which I'll give you about a week, probably a little more than a week, just so there's not too much overlap, which is on an important change in logic fabric. So Stratix 2 is an architecture that brought in a new kind of logic element that since has become the most common kind. Not everybody uses it, but most FPGAs use some variation on it. Okay, so concept map, where are we? Okay, so we just went through FPGA architecture styles, so we're like now deep diving into what's inside these chips. And for the rest of this lecture, and probably the start of next one, we're talking about how do you actually build some of these structures so you can get a sense of how we estimate their area and delay. Well, a particular area. Today I'm not going to talk much about delay. Okay, so to do that, we're going to do an example. So most FPGA architecture results come from a complicated CAD flow. So you take a CAD flow and you implement a bunch of circuits in a proposed FPGA architecture, and you estimate the delay that each of them is going to have, so their maximum clock frequency, and you estimate the area of the FPGA that you'd need to accommodate them, and you come up with answers of this is better or this is worse. So that's how you do this for, to get answers you really trust. But in order to understand, it's kind of a black box too, right? Unless you write those CAD tools to develop those area models and delay models, you don't really know what's going on when you read one of those papers. So what we're going to do is to gain insight, we're going to do a simple analysis by hand, okay? We're going to see how to build the relevant circuitry. We're going to estimate its area, and FPGAs are typically transistor dominated. Okay, so most chips now are actually wiring dominated, where that's what limits the, how much you can pack on a chip. FPGAs, because they use so many transistors to build lookup tables and the programmable routing, they're usually dominated still by transistors. The wiring matters, like you could run out of wires, but usually with a properly chosen routing architecture, it'll fit over top of the transistors. So we're going to estimate our area by looking at what transistors do we need. And one of the things we want to see is, okay, so we're going to see how do we build it. Then we're going to estimate the area by estimating how much area would these transistors take. It doesn't have to be a perfect answer, because we're going to use this to kind of compare architecture options and get insight. And we want to see also how much area goes into the logic versus the routing, because that's an important thing to understand. Like what's really important when we're optimizing an FPGA? Is it about the logic? Is it about the routing? Okay, so the way we're going to do this is we're going to take a simple architecture. 1 4-LUT per logic block. So we're not doing that hybrid hierarchical FPGA architecture with the local routing. We're just 1 4-LUT per logic block. All of the it's going to be island style, but all of the routing wires are going to be length 1. So they go past one block, then you got to go through programmable switches to keep going. And all of the routing switches are made out of multiplexers, which is the most common way to build routing switches. So simple FPGA, but it's not a crazy one. Okay, so this is what our basic architecture looks like. Island style FPGA, we've got a 4-input lookup table. So 4 inputs, 1 output. Didn't bother putting a register in. Okay, so you probably should put that in if you went to make this for real. We have, this is the repeated layout unit. It's called a tile. Okay, so it is this 4-LUT and the piece of channel to its right, and the piece of vertical channel to its right, and the piece of horizontal channel below it. If I was to replicate this over and over and over again, I would get all the lookup tables and all the routing channels of an FPGA. Does that make sense? Because this is like the basic repeating unit. What's in this unit? Well, there's a lookup table. I have multiplexers that let me pick which routing track connects to each input pin. So I got 4 input pins. So 2 of these are connecting, I'm showing 2 of them connecting to the vertical channel beside me and 2 of them connecting to the horizontal channel. And if I want to have some flexibility in how do I get here, I don't want to just connect one of these routing wires up to this input. I want to have a multiplexer. Okay, so there's a multiplexer here letting me choose. I also need to have the ability to choose, well, how do I get the signal out of this logic block into the programmable routing? And I'm using multiplexer-based switches. So what I do is I have a multiplexer here that's driving a routing wire. So every routing wire is going to have one multiplexer driving it. I'm just showing one of them, but each one of these will have a multiplexer in front of it. this lookup table can drive into this multiplexer. Also, these other routing wires can drive into it. So that allows me to select how am I connecting things, right? I can connect my outputs into the routing channels. I can connect wires to each other so I can go long distances. And then at the other end of my route, I can get into the logic block by going through this mux. Okay, so does it make sense? So this would be a fully functional combinational FPGA. So I don't want to analyze the flip-flop area because it's relatively small, but if I really built this, I should probably put flip-flops in. Yeah? You're saying this mux, should I also have it on these other inputs?
No, as like if you want, you could use the mux to connect to the output. Sorry, the mux spec into the
This one?
yeah.
Okay.
You could use like upstream of that at the time. You could use this to switch tracks between vertical and horizontal.
Yeah, yeah.
The LUT or like basically all inputs of the LUT could be fed by the vertical channel if you want.
You could. Yeah, there's no, I just drew it this way, right? So the way I drew it, I haven't drawn everything, but I probably have a mux here that allows me to connect these to horizontal channels. It's not the only way I could do it. I could say, nope, I'd rather this guy connects to the vertical channels, put a mux here. Does that make sense? I could even make a bigger mux that took signals from both of them. All of those things are fine. And I think I basically decided just to connect to one of the channels that comes by, but connect to every wire in it, which is a reasonable choice, but not the only choice. Does that make sense? And again, I haven't shown it, but every single one of these routing wires, like this one as well, would have a mux in front of it. Okay, so I'm only showing kind of a piece of this, so it's not too complicated. Yeah?
So is like the selection of the mux determined during configuration?
Yeah, I haven't shown it here, but this mux would have a couple of SRAM cells anyway. So there's some SRAM cells that would control this mux. Same thing here. Does that make sense?
So like the logic cannot
Logic doesn't control these muxes. These muxes are configured when you power up the FPGA, you read the data in from, say, a flash chip. And yeah, the CAD tool chose what all these bits should be, and now you're reading them all in. Does that make sense?
if we can change the selection of the like
So you're saying, what if I just said maybe the output could also control these? People have actually proposed that. So if you want, for your term paper, you could go look at that. People have said, hey, multiplexers occur all the time in designs. So they actually turn out to be a significant fraction of the typical design's logic. And we have all of these routing multiplexers. Couldn't I use those to implement the end user's application? So people have actually tried that. The basic problem is it's really hard to route. If you start using your routing multiplexers as logic, you kind of go, well, who connects my, if I use my routing multiplexers as logic, what do I use to allow me to connect my signals together? And it starts getting kind of hairy. Does that make sense? But it is possible, and people have looked at it. No commercial FPGA that I know of actually does it, because it gets hard to do. Maybe I shouldn't quite say that. I mean, Efinix is a company that is a smaller company that makes FPGAs, and they have some ability to change. They do blend logic and routing a bit. So if you look at the details of their architecture, they might be able to do a bit of that. Yeah.
I think for the like connection between the rooftop table and the multiplexer, I think that would like because as a designer, like we want to guarantee the functionality, like the correctness of the design, right? So I think the rooftop table itself is not smart enough to like to determine.
Oh, well, the CAD tool chooses this. The CAD tool will choose what SRAM bits to put in here based on what it programs these SRAM bits to be. So this is a 4-to-1 mux. So I could control it with 2 SRAM cells. Maybe I'll use more, but I could control it with 2. So if the CAD tool programmed in, whoops. Okay, I don't know what I just did there. Let's get out of there. If CAD tool programmed in, for example, 0, 0, that would indicate that this routing wire should be driven by the output of the LUT. And the LUT doesn't pick. Wow, okay, let me see if I can get out of this. I did something that my Surface does not like. Okay, good. Okay, I'm back. So if that was 0, 0, programmed by the CAD tool, let's say that this signal is the 0, 0 input to the mux. The LUT will go through that mux.
I mean, I agree with this RAM method. I just I think like if we allow the output of the lookup table like logic unit to connect to the multiplexer.
You mean to control the multiplexer? It does get hairy. The idea of that is that it, yeah.
I think we can use more like complicated or more smart like the CPU small CPU to control like
You could try that, but all this stuff costs area. If you started putting a CPU in to control every mux, then that's going to be big. So.
dynamic configuration is a good idea. But
Okay.
I think logic unit is not smart enough to make that easy to change the configuration.
I think maybe we'll take it offline, right? So I'm just going to, because I'm not sure if I think you're talking about dynamic reconfiguration, which we'll talk a bit about later, but it's probably a bigger topic. Okay, so this is our basic FPGA that want to estimate the area of these components to see how big are they compared to each other, how do we build them. Okay, so how do we estimate area? Okay, so various things have been done in the literature. So you could count switches. Okay, so counting switches means I go back here, okay, that's a switch, that's a switch, that's a switch, you know, that output is a switch, 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 etc. So I could count all these edges and say that's my switches. What do you think? Do you like that as an estimate? People have done this. So is it a good estimate of area or not? And only if we're just trying to compare one architecture with another, it doesn't have to really give us area. It just has to correlate with area. So I'm not saying that counting switches would give you like some number in square microns, but if counting the switches used by one architecture versus another to implement a bunch of designs, you know, is that a reasonable way to try to compare whether that architecture is better than the other one? So what do you think? No one has an opinion. So people have done this. I mean, it's better than nothing. The downside of it is if I counted switches here, I could do things like, for example, put a flip-flop in here. And it has no cost if I didn't put a switch in. Or I could put, you know, instead of a 4 LUT, I could put a whole bunch of gates in here as well. And as long as I don't put any switches in, or maybe I just put one in to turn it on or off, it appears to have no area. So switches isn't a great idea. It's okay as long as you're not changing very much. But if you actually start putting in significant amounts of non-programmable logic, it looks free if you basically are only counting switches. So while people have done this in architecture studies, it's not a great idea. So what about counting transistors? Is that better? Okay, so this is basically not great. So if I count transistors, well, adding more multiplexers is going to cost me transistors. If I start putting, you know, some extra AND gates in here and stuff, well, that'll cost transistors. So there's kind of nothing I can put in that's free anymore, which is good. Whoops. So I'd say it's better than counting switches, because at least you're counting all your transistors, whereas switches were just kind of counting some of your transistors. What do you think?
Still, wiring take a lot of
Yeah, the wiring could take a lot of area. Now, I am assuming, and this is pretty common, that I'm going to be limited by transistors, and the wiring is going to fit above it. You can make architectures where that's not true, so it's good to keep an eye on it. But it's common that the architecture is dominated by transistors. So this is not bad. It's better than counting switches. Okay, so it's better. But estimating layout area would be better still. Why? Because not all transistors are the same size. Okay, so some of the transistors, like in the transistors in these SRAM cells, okay, so I got SRAM cells controlling this, I can make those very small, typically minimum size, because their speed is not important, right? They just sit there in the same state forever. There are going to be some transistors that are driving this routing wire. This routing wire is relatively big. Even if it only goes past one logic block, that's still reasonably big. I need to have a fairly big set of transistors that are actually driving it. So not all my transistors are the same size. So layout area is better still, because you try to estimate, I have some big transistors, I have some small transistors, rather than just saying they're all equal. Okay, so it's better still. Okay, this is still better. What about completing a layout? So forget about estimating a layout. What if I just complete the layout and then measure it? So what do you think? Best estimate? So any thoughts? You like this? What do you think?
I think it's a trade-off between like like how precise, like you mentioned.
Yeah, so this is definitely a trade-off. If you said it's the best method, totally unqualified, then I totally want to take you on as a grad student because you could just evaluate a whole bunch of architecture ideas for the next 200 years, right, without complaint. It is the most accurate method, but it's extremely time-consuming. So the number of different architecture ideas you can evaluate is very small. And it gets so time-consuming that also is a problem. Because if you just say, well, this should take me, I don't know, a year to fully optimize this layout, but I'm going to do it in 3 days, well, then how good is your layout? Maybe your layout is actually not any better, or maybe it's even worse than just guessing how much area the layout would take based on transistor count and size. So yeah, in a world with infinite time and infinite resources, this would be the best. In practice, you can usually only do this for a final few candidate architectures in a big company. So when I was at Altera, we would evaluate most architectures at this point. We'd estimate layout area using some, and this is what most academics do as well, using fairly quick metrics that you can compute easily and are not too bad. And then most academics, you end there, right? That's your answer. If you're a company like Xilinx or Altera, what you usually do is the last candidate or 2 architectures or 3, you will do some sample layouts and kind of go, okay, let's fine tune. But you can't afford to do that for very many of them. And academics can't afford to do it usually for any of them. So yeah.
If you want to use the catch tool to measure the area that you need, like
Oh, so that's a good question. Okay, so this is maybe an important thing to understand. So what I'm showing you here is like an FPGA tile. And I'm going to show you how this is commonly built. Okay, like one set of circuit structures. And those circuit structures are full custom. Okay, so they're somewhat dangerous circuit styles. And you're doing transistor level design and optimization. The ASIC CAD tools are built around standard cells. Okay, so don't do transistor level optimization. The transistors have already been grouped into like, you know, a flip-flop, an AND gate, a MUX. And they're in what are called safe circuit styles, like safe CMOS styles where you can combine those gates together and they always work. You can build an FPGA that way. And if you do that, there are actually automatic tools that will do it for you. They wind up with an FPGA that's typically 2 to 3 times bigger and 2 times slower than if you had done it with full custom design the way I'm going to show you. Does that make sense? So it's in that case, where you use standard cell ASIC tools, you can get an answer pretty fast. Okay, there are tools that basically can automatically set up the FPGA net list essentially, and you can then get an answer. It still takes a while for the ASIC tools to run, but you can get an answer in maybe a day or a week. Whereas what I'm going to show you to lay out by hand, it will take you probably months. But you will get an answer that is, you know, maybe 2 to 3 times more dense and twice as fast. Does that make sense? So if you're trying to build, if you're Intel or Xilinx or AMD, you're going to build it full custom because you want those gains, which means you want your area model and delay model to estimate what you will get full custom. Does that make sense? Yeah.
Is there a correlation between the automated flow that he mentioned and the custom flow? Because if the automated flow is always 5 to 6 times worse, we can just do that and increase the estimate by 5 to 6 times.
It's a good question. Nobody knows. I've never seen a study that did that. That's a good idea. Okay, so I'm actually going to talk to somebody at CMU who has one of these flows because he's looking for collaborations. That would actually be a very good idea. So that should be done. I actually don't know anybody that's done it. So, because you're right, if they correlate well, then it's fine. They probably won't correlate perfectly because the cost is not the same for every building block. Basically, the full custom style I'm going to show you is particularly good at building multiplexers. And the configuration RAM is also pretty efficient. So I guess there probably will be some correlation, but also some misalignment. Does that make sense? Okay, so I'm going to show you a model that is commonly used, not the only one you could use, but commonly used to go from transistor, basically transistor count plus size You need two things: how many transistors and what are their sizes, into an estimate of area. And it assumes that you're limited by the transistors, not the wiring. Okay, so you'll see it in a bunch of literature. It's called the minimum width transistor area model. So what it means is there's a certain minimum size transistor that you can make in any manufacturing process. And that's what I'm showing here. So this transistor, this is the width of a transistor. Okay, so how wide is the diffusion? This is a bulk process, so it's not FinFET, but the analysis is similar in FinFETs. So there's a certain minimum width you can make and still put contacts down to that transistor. Then you have to have a gate, and the gate needs to have a certain distance from those contacts, and so on. All right? Then there's a spacing rule before you can make another transistor. Okay, so there's spacing rules here. So you take this whole thing, and it basically defines how much space do I need to make the smallest transistor I can, including the space to the next transistors and the ability to actually connect to it and so on. Okay, and we don't really care how big this is in microns. We just define that to be kind of a unit, right? If I make a really small transistor, it takes 1 unit. Okay, all my transistors aren't going to be really small. Some of them are going to need additional drive strength. And the way you get more drive strength is you can basically increase the width. So here I'm making the diffusion twice as wide. And that basically gives me twice as much current through this transistor, which if I'm charging a certain capacitance makes my circuit twice as fast. But it increases my area. I can also parallel my transistors. So here, instead of making my width making it twice as wide, or in FinFETs, making twice as many fins, I've basically made 2 parallel diffusions. Okay, so I make 2 gates. So these 2 gates, this is basically, my input, this is my input, this is my output. I have 2 transistors pumping current into the output, so I also get twice as much current. So I can do either one of these things. If I need to get a transistor that has twice the drive strength, because when I sized things, I decided that was I needed that for speed. I also can combine these, right? So I could, if I need something that's like 4 times the drive strength, I could do both these things, and so on. So if you take all of these options, a very simple area model is the area to get a certain drive strength X. Okay, so there's a minimum drive strength, which is the smallest transistor that you can make, has this amount of current. If I need just that smallest unit, 1 of drive strength, then the area is also 1. If I needed to have twice as much drive strength, then X is 2, and the area would be 1.5. Okay, because the reason is I don't need to increase the spacing, I don't need to increase everything. I just needed to increase the width, or I needed to make parallel diffusions. But to get twice as much drive strength doesn't take me twice as much area. Okay? So in this model, twice as much drive strength took me 50% more area. If you want more accurate than this, you can see this paper. It's one of the assigned reading papers, which gives a more accurate formula that's a bit more complicated. I don't want to do on the board. It doesn't change results a lot. And this paper actually goes through and does a whole bunch of layouts to say how accurate is this. And they said it has some correlation, but it's definitely imperfect. So it's not everything, but it's enough to do a lot of studies. Okay, does that make sense? So that's kind of what you need to know. And let me just check what's going on in the chat here. Oh, okay, that's just a statement. Everything's okay. Okay, so let's turn the projector off. And get rid of this. Okay, so I definitely will not get through everything today, but I basically now want to go and design the low-level circuitry of my simple FPGA and use my simple area model to say how big are these things. So we get some insight into what's big, what's small, also how do we design some of this stuff. Okay, so we're going to make a transistor level schematic. And we're going to start with the lookup table. So we had a 4-input lookup table there. I'm not going to draw all the transistors for a 4-input lookup table. I'm going to draw a much smaller lookup table. Okay, so I'm going to do a 2-input lookup table. So I got 4 SRAM cells. That's my truth table. And then I need to have a 4-to-1 mux, right? Controlled by my two inputs. And the usual way this is done in an FPGA is like this. Okay, so FPGAs use a lot of pass transistor logic. So I don't know if you've seen it before, but it can be efficient for things like multiplexers. It's a slightly more dangerous circuit style, where if you don't come to it carefully, things won't work, which is why ASIC tools are not going to use this. All right, it's too dangerous, but humans can use it. Okay, so let's see. So I got a control signal here. Okay, so here's my first input. Okay, let's see if I can draw this properly. Okay, and this one goes over here. This looks more complicated probably than it really is. I'll walk through it in a second. Let's see. Okay, so that's my my lookup table. Okay, so I need 4. This is just a 2-input lookup table. So I need 4 SRAM cells to store, the data values, the truth table, and then I need a 4-to-1 mux, and this is a 4-to-1 pass transistor mux. Okay, so this pass transistor, if input 0 is 1, this pass transistor will be on, and this data will flow through here. If input 1 is also 1, this pass transistor will be on and data will flow to here. Okay, it'll be inverted and sent out. Okay, don't worry about the inversion, right? I could always put another inverter out here, but I'm not going to bother. Okay, if input 0 was 0, this pass transistor is on, and if input 1 was 1, then this pass transistor is on. Data will flow through here. Okay. And this one's off, so nothing's going to come through here. And so on. Okay, so when input 1 is 0, this transistor's on, this transistor's off, so we don't care what's happening up here, we only care what's happening down here. And if input 0 was also 0, so if this was 0 and this is 0, I turn on this transistor, and whatever I stored in here makes it out to my output. Okay, so does that make sense? So no matter what I put on input 0 and input 1, there is only one path that will go through 2 pass transistors from one of these to the output. Okay? Half of them are going to make it, does that make sense? So only one thing makes it all the way through this pass transistor network. Yeah? Sure.
Is that, what is the last part?
So what's at the end?
Yeah, is this the last part?
Yeah, so that's a good question. So I'm going to talk about that in a second. What's your second question?
Yeah, second question is that you say for in VLSI design, like we rarely use this pattern as standard.
You use it in full custom design, which is what this is. Full custom meaning I'm actually laying out transistors. So you can, because FPGAs use this extensively. All right. When we talk about this, you'll get some insight maybe into why this circuit design is a little more dangerous than standard cell tools usually like. Okay? So yeah, when you use standard cells, you give up some flexibility. That's the way ASIC tools work. Okay? So they don't really place transistors, not automatic digital logic implementation tools for ASICs. They don't really place transistors. They place standard cells, so AND gates, flip-flops, muxes, and then they wire them together. And inside those standard cells, they won't use pass transistor logic. Well, it would be rare because it's considered dangerous. Okay? But for a human analyzing this, you can make it work. It's not just that it's dangerous. It also makes timing analysis, like saying how fast it is, more complicated. So ASIC tools don't like that. So they give up some optimization in exchange for doing a lot of work for you. But FPGAs, because we're making, we're going to make this lookup table and they're going to repeat it, I don't know, 5 million times. So that is actually worth optimizing. Does that make sense? Actually, was there another question? I'll go on to your second question in a second. Okay, so your other question is, okay, so I think everybody's then with me with this part. Is that right? SRAM cells, pass transistor multiplexer. And then we go, okay, what the heck is this? Well, okay, this pass transistor multiplexer has low drive strength. I went through one transistor here, another transistor here, and I'm going to go hook this up to who knows what. So it would be a bad idea to connect it directly, right? I should put an inverter here, or I could put 2 inverters in series and make a buffer. But I don't want to expose a big capacitive load to these pass transistors because that makes what is already kind of a dangerous circuit style super dangerous, okay? Like connecting up to a big capacitance. And it'll be slow because these pass transistors, connecting 2 transistors in series like this, if you think of them as resistors, which is to first order correct, it's like you've doubled the resistance, all right? So the more pass transistors you have in series, the less capacitance you want loading them because they're gonna charge and discharge that less efficiently. So I want to have this inverter here so that I'm isolated from whatever I'm driving. So that's the first thing. Then, but what the heck is this? Okay, and the other thing I should tell you is this is a weak transistor. Okay, so I intentionally make this transistor as small as I can. I also usually make its channel longer than the minimum. And remember that transistor current is proportional to width divided by length. Usually we use the minimum length, okay, because why not? Smallest area gets more drive strength. And then W you have to think about, right? Because it costs you area, but it gives you more drive strength. For this one, I'm going to make W small, and I'm actually going to make L bigger than the minimum because I want this to be weak. Okay, what is this for? Like, why did I put this here? I'm going to repeat this 5 million times, so I don't really want to have any transistors that I don't need. So, but I need it. Yeah, what do you think?
So that's reinforcing the relatively weak signal that's passing through the 2 resistances. So that's acting as like a pull-up, basically.
Yeah, so this is a weak pull-up. So it is a pull-up. So basically, if this is a logic, okay, let me see, I have to think about this for a second. If this is a logic 0, okay, then this is going to turn on, and it's going to pull this node up, which is going to reinforce that this is a logic 0, because there's an inverter between them. If this is a logic 1, this is going to turn off, okay? So it doesn't do anything like a logic 1, but it does do something like a logic 0 on the output. Okay, why do I need that? Okay, so pass transistors, these are NMOS pass transistors. So if an NMOS pass transistor, let's see, did I actually write any of this down? Okay, we'll see if I make any mistakes while I'm doing this. If I put this waveform, okay, so say this is V in, and I got a pass transistor, so V in here, pass transistor, and V out, and I've got a logic 1 here. Okay, so that's VDD. So I've turned this pass transistor on. I put a certain V in. What do I get as my V out? Okay, when V in is 0, a pass transistor can transmit a 0 well. Okay, so your V out looks like that. When you put the 1 in, obviously there's some delay, so it's going to take a while to climb up. But let's say this is a 1 volt process. This output will not go to 1 volt. It'll go to maybe 0.7. Okay, it'll be down by a threshold voltage. Okay, so you have to go back to your transistor level courses from perhaps second or third year. Basically, you need VGS to be greater than VT for this transistor to be on, okay? And once both terminals of this, basically once this terminal goes to 0.7 volts, and this one is at 1 volt, you have a VGS of, say, 0.3 volts, and that's equal to your threshold voltage. This turns off, okay? So it will not take you all the way to VDD. It will take you down all the way to ground. It can pass a logic 0 perfectly, but it can't pass a logic 1 perfectly. It degrades it. Does that make sense? If I pass, okay, so is everybody with me on that? This might be a while since you studied this, but this is one of the things that makes pass transistor logic dangerous. It doesn't transmit clean logic 1s. Does that make sense? Okay, so if I took that 0.7 volts and I just said, oh, I'll live with it. I'll put it into this inverter. Okay, the inverter is an amplifier, so it actually will tend to amplify this, so the 0.7 will probably come out to be approximately 0, but maybe it only comes out to be 0.1. Right? It's going to invert it, and it's going to tend to amplify. So that's not great. You know, my logic 0 is going to come out. After inversion, I may still not be at 0. But even worse is inside, this is the real killer for this, inside that inverter, I have this structure, right? This is my input, this is my output. So all CMOS is designed so that there's never a DC path between power and ground. Okay, so if I put 1 volt here, this is strongly on, this is completely off. Okay, no DC path. I put a logic 0, this is completely off, this is strongly on, but there's no path that just sends current down here. If I put a 0.7 volts into here, okay, this is pretty on, mostly on. This is just barely off, okay? It's actually got a VGS of 0.3 volts, which is enough that it's almost on, which means it's leaking like crazy. And it's really sensitive. It turns out that for some other second order effects, this 0.7 might actually only be 0.65, okay? And that means this is actually truly on, you know, not the strongest on. Okay, this, for one inverter, that's some power. If you multiply that by 5 million inverters, it melts your chip. Okay, so you can't do this. You cannot allow this signal to sit at 0.7 volts. So what happens is when the signal is rising to 0.7 volts, so it's going through, it's rising, it gets to 0.7, this output is nearly 0, okay, because this is an amplifier. This turns on. Okay, and it pulls it the rest of the way up. So it'll keep going and go all the way to logic 1. The downstream logic has already been passed pretty much as 0. So this last part doesn't really cost you much delay, but it guarantees that you're not leaking current like crazy. You have to make this relatively weak, because when you then, you know, input 1 changes, and maybe you connect to a different, you know, SRAM cell, so maybe this signal now goes to 0 because you just changed, right? A new input's come in, you got a 0. This goes to 0, this is still trying to hold it up. Once the 0, if you pull it down close to 0, this will start putting a logic 1, which will turn this off. Okay, so it'll stop fighting as soon as this 0 turns this output into a 1. But you need to make sure that this path through 2 pass transistors has lower resistance than this path through 1 pull-up. Otherwise, this will never switch. You made a latch. It'll just stay there. Okay, that's also not good. So this has to be made weak. Does that make sense? Yeah?
Does a weak transistor mean that compared to that last stage and most transistors,
Yeah.
its current driving capability is vastly less?
It has to be quite a bit less. So basically, I have to essentially double the resistance of these to account for the fact that there are 2 of them. They also are, they get relative, they're barely on as they approach this 0.7 volts, so they're weaker still. So you would want this to be, you know, significantly more than twice as weak as one of these. More like probably, you know, 5 times weaker than one of them. You'd actually do a bunch of SPICE simulations to see what seems good, but you want it to be pretty weak. Does that make sense? Yeah? Yeah.
Does it like make sense because we invert the output?
Yeah, so if you want, you can put another inverter right here. Okay, and that's actually pretty commonly done because this inverter would be usually pretty small. It's pretty small because you don't want to load this with much capacitance, and the bigger you make these transistors, the more gate capacitance they present. But you're often driving, say, some local interconnect. That local interconnect has a fair amount of capacitance. So you actually make a second inverter that's relatively big. And that now can drive that. So this is a standard technique in full custom design as well. I have something that's relatively weak. I put a small inverter so I don't load it very much. That small inverter has more strength. Now I can put a big inverter and that can drive something quite large. So I'm scaling up my drive strength. So I'm not going to do it in this analysis because I'm just trying to keep it simple. But often there is a second inverter here. But in fact, usually there is.
I always saw the design like a small inverter and a bigger inverter connect together. Like
Yeah. So that's a common technique because you're trying to increase, it's called stage ratio. You're basically trying to increase your drive strength. And the best way to do that is basically if you actually go and analyze what minimizes your delay, it's basically that you're gradually increasing the size. If you've got to drive a big load, you gradually increase the size of the inverters that are driving it. And it's so that no one stage is loaded too much. Because you'll be really, if you make something that's got weak drive strength, so this has really weak drive strength, and you load it a lot, it's really slow. So you're trying to keep that load small and then gradually build up to drive a big load. Does that make sense? Okay, so this is my lookup table. So FPGAs usually use pass transistor logic for this. It's getting trickier because VDD keeps going down, and threshold voltages also are going down, but it's hard to keep them going down at the same rate. Okay, so if your threshold voltage becomes a bigger part of your VDD, well, then this gap gets bigger, right? And that makes this harder to design. What happens, but there's a safer version of this where you replace every one of these pass transistors with a pair of transistors. You basically put a PMOS in parallel with it. Okay, that makes something called a transmission gate that you might have studied before. The transmission gate, because it's got both a PMOS and an NMOS, can transmit both a logic 1 and a logic 0 cleanly. So that's the next best thing. It is significantly more expensive, though, because you just doubled the number of transistors in this MUX tree. So if it works, FPGAs will do this. For some of the most advanced process nodes, where VT is a larger fraction of VDD, just so you don't have too much leakage, you may have to switch to transmission gates. And the second paper that you were assigned last week talks about that. So it kind of analyzes like where is that trade-off. It doesn't fundamentally change how you build this though, right? You basically wind up doubling the number of transistors in this tree, but otherwise it looks pretty much the same. Does that make sense? Okay, so that might be more than you wanted to know about LUTs, but the whole point of this was to try to get an equation of how many transistors do we need so we get an area estimate. Okay, so number of transistors. So let's get that first. Okay, so we need the SRAM cells. So in this case, I have 6. So a standard SRAM cell takes 6 transistors. Okay, and we'll look at block RAMs in another couple weeks, so you'll see that, why that is. But it's cross-coupled inverters plus a couple of access transistors. So an SRAM cell takes 6 transistors. And in this 2-input lookup table, I needed 4 of them. I also have 4 plus 2 pass transistors. Okay, so I have 6 pass transistors. This was SRAM. I have 1 inverter for each of my inputs because I need the true and the complement so I can control all my pass gates. And I'm going to erase this one. So I'm just going to show the little inverter. I have 1 inverter on my output. So that's 6 transistors in my inverters. And then I get 1 transistor here for this weak pull-up. Okay, so I get 1. It's my keeper transistor or weak pull-up transistor. So for this 2-input lookup table, I have 37 transistors. Okay, so if I do this in general, so this was for a 2 LUT. For a K LUT, all right, so what's the general, let's generalize this. So how many SRAM cells do I have in a K input lookup table? So it's 4 in a 2 input lookup table. What is it if I have K inputs? Right, so 6 transistors times 6 transistors per SRAM times 2 to the K. Okay, what's the general rule for how many pass transistors I have for a K input lookup table? Okay, so, yeah, very good. I had to look at my notes, or I would have had to go derive it. So 2 to the K plus 1, almost. It's 2 to the K plus 1 minus 2. Okay, it's a geometric series. Okay, so I get 2 to the K in the first stage, like 1 connected to every SRAM cell. Then I get 2 to the K minus 1 in the second stage, and so on. The sum of a geometric series like that would be 2 to the K plus 1 minus 1, if you remember your sums of geometric series. But I take the last, the last stage would be just a single pass transistor that's always on, which there is no purpose in doing that. So you take that out and replace it by a wire. That's where you get the minus 2. Okay? And then if I take, okay, the number of inverters, I need 1 for every input plus 1 for the output. So generalizing that is pretty easy. So it's 2K, 2 transistors per inverter. I need K of them, plus 1 more, plus a keeper. So 2K plus 3. Okay, and that's basically inverters plus keeper. Okay, and we see again it's exponential in K, which we saw before. We looked at, are any of these logic elements really scalable? And we said the LUTs grow exponentially. We can see that when we count the transistors. So that's kind of comforting. That's good. Okay, the last thing I want to do is, so we've gotten a transistor count, which is a not terrible area model, but we'd like to do a bit better. So let's say we're going to do a 4 input lookup table, and we want the pass transistors to have 5 times the minimum drive strength. So 5 times the minimum. All right, so the SRAM cells, you can use really small transistors. They're just holding state. There's no speed requirement on them. This first inverter I want to be pretty small. This I want to be very small. So what's left? These pass transistors, I need them to be stronger than this, and how strong they are also impacts my speed. So it's worth spending some area on them. So I'm going to decide that I want them to be 5 times the minimum drive strength, which is like a reasonable number. If you were doing this, you would actually go spice this or use a tool that knows how to spice this kind of circuitry. But I'm telling you 5 times minimum drive strength is reasonable. If I take that and I plug it into this formula, and I use the fact that, let's see. Remember I gave you that simple formula of the area of a 5 times drive transistor is equal to 0.5 plus 0.5 times the drive strength, which is 5. That means this area would be 3. Okay? So it's 5 times the drive strength, but the actual area I need, including the spacing to the next transistor and everything, is only like 3 times bigger. If I plug all of that back in there, I would get the area is equal to 217 min width transistor areas. Okay, so this is like a process technology kind of independent number. It's like I need like 217 of the smallest transistor areas I could make that are kind of useful. Okay, I think we'll end there for today. So where we're going to keep going at the start of next week is that's a 4 LUT, right? Now we need to do this for the routing muxes, and we're going to see how big is the routing compared to the LUT to get a bit of insight. Okay? If there are any questions, come up and ask me. I'll let everybody go. So.